video, we are going to discuss about logic gates. Logic gates are electronic circuits that operate on one or more input signals to produce standard output signal. Usually, logic gates will be having more than one input and only one output. Logic gates are classified into three types. One set of gates are basic or fundamental gates. Next is universal gates, and the third set of gates are derived gates. Example for basic or fundamental gates are AND gate, OR gate and NOT gate. For universal gates, the examples are NAND and NOR gates. Derived gates examples are XOR gate and exclusive NOR gate. Let us see one by one. First, AND gate. AND gate performs logical multiplication. This is the symbol of the AND gate, and this is the truth table. See here, as you see, the output is A dot B. So here the possible combinations are 0, 0, 0, 1, 1, 0 and 1, 1. So just multiplication. So you will be getting 0, 0, 0 and only 1, 1. Means when A and B are 1, output is 1. In all other combinations, it is 0. Next gate is OR gate. OR gate performs logical addition. The output signal is 1 if at least one of the input signal is 1. This is the symbol of OR gate, and the boolean expression or the output expression is A plus B. Then this is the truth table. Here, when both inputs are 0, output is 0. In remaining all the three combination, output is 1. Means if A or B is 1, output is 1. Next set of gate is NOT gate. NOT gate performs complementation operation. This is the logical symbol of a NOT gate. It has one input and one output. The boolean expression or the output expression is A bar. If the input is 0, your output will be 1. If the input is 1, then the NOT gate output is 0. These are the three basic or fundamental gates. Next set of gates are universal gates, NAND gate and NOR gate. NAND gate means AND gate with NOT, that is complemented AND gate. And this is the symbol of a NAND gate, AND gate and with a bubble in the front. And the boolean expression is A dot B the whole bar. Otherwise, by De Morgan's law, it is A bar plus B bar. And the truth table is like this. Here, as you see, if any one input is 0, your output will be 1. That is 0 into 0, and then we are taking the complement, so it becomes 1. Similarly, 0 into 1 is 0. When you take the complement, it becomes 1. 1 into 0 is 0, complement is 1. Similarly, 1 into 1 is 1, the complement is 0. That is the truth table of a NAND gate. Next is NOR gate. NOR gate is complemented OR gate. OR gate plus NOT gate. And this is a logical symbol of a NOR gate. And we have a bubble, OR gate with a bubble. The output expression or the boolean expression is A plus B the whole bar. That is A bar dot B bar as per De Morgan's law. And the truth table is like this. So if any one input is 1, your output is 0. Just the opposite of OR gate. 0 plus 0 is 0, the complement is 1. Similarly, 0 plus 1 is 1, the complement is 0. 1 plus 0 is 1, complement is 0. 1 plus 1 is 1, the complement is 0. And using AND, OR and NOT gate, you can have any boolean expression. Means any boolean expression can be implemented using these three gates. For example, if I have this gate or this circuit, here as you see, this is a NOT gate, and NOT gate output will be A bar, and this is OR gate. OR gate output will be addition. So B and C are the input. So you are getting B plus C. here it is AND gate. AND gate performs multiplication. So A bar dot B plus C. This is what the output expression of this circuit. Similarly, let us take another example. Here this is OR gate. OR gate inputs are A and B. So the output will be A plus B. Similarly, AND gate output is multiplication. So A dot B, and we have a NOT gate. So it will be complementing this input. The input is A dot B. So A dot B the whole bar. Now again we are using AND gate. AND gate means multiplication. So A plus B dot AB the whole bar. Similarly, if the boolean expression is given, then we can implement using these three gates. So for example, I am taking this expression A dot B plus C, just a AND gate we need because it is multiplication, then plus C. For that we need an OR gate. So A dot B plus C. This is what the circuit for this expression A dot B plus C. Let us take another example. A dot B the whole bar plus C dot D plus E dot B the whole bar. So A dot B means we need an AND gate, then one NOT gate, so that you will be getting A dot B the whole bar. Similarly, C dot D another AND gate because it is multiplication, C dot D. Then the third term E dot F the whole bar. So E dot F we need an AND gate, then for complementing we need an NOT gate, E dot F the whole bar. So that now again all the three has to be added. So we need an OR gate here. Sorry, it should be an OR gate. So we need an OR gate here. Next, this NAND and NOR gates are called universal gates because this NAND gate alone is sufficient to implement any set of boolean expression. Similarly, NOR gate is also sufficient to implement any boolean expression. That's why NAND and NOR gates are called universal gates. So let us see how we are going to implement the basic gates NOT, AND and OR using this NAND gate. So NAND gate has two inputs. Now NOT gate needs only one input. So what we need to do is simply just short both inputs. So if I give the input as A, then it will multiply and takes the complement. So A dot A the whole bar, A dot A is A. So A bar you will be getting. Or by De Morgan's law, A dot A the whole bar is A bar plus A bar. Again A bar plus A bar is A bar. For AND gate implementation, we need to have another one NAND gate as a NOT gate. So first A dot B the whole bar. AND gate means we need A dot B. So just another inverter. Here we are using a NAND gate as a NOT gate. So A dot B the double bar. So you will be getting A dot B. Similarly, to implement OR gate, we need to have three NAND gates. So there's one NAND gate here as a NOT gate. So here A, when I give the input, then I will be getting A bar. Similarly B, if I give the input, I will be getting B bar. Then again we are passing this A bar and B bar through a NAND gate. NAND gate, what it will do is just multiply the inputs and takes the complement. So the inputs now are A bar and B bar. So it will multiply both A bar dot B bar the whole bar. If I apply De Morgan's law, it will be A double bar plus B double bar. That is nothing but A plus B. And any expression we can implement using NAND gate. Let us take one example. A dot B bar plus C into A plus B dot D. So here first step is we have to implement using AND gates and OR gates. So A dot B bar, A and B bar we have to give through a AND gate. Then B and D another AND gate, multiplication. B dot D is multiplication. Then we have to add with A. So addition means we need OR gate. A plus B dot D. Then again that should be multiplied with C. So again another AND gate. C dot A plus B dot D. then the total, this A dot B bar and this term must be added. So we need an OR gate. This is the first step. In the second step, here all the gates has to be converted into NAND. So for that, for AND gate, we have to add bubble in the output side. We have to complement in the output side. So if I put bubble in the AND gate, then it becomes a NAND. Similarly, bubbled OR is NAND. So we have to put bubbles in the input side of OR gate. Input side of OR gate. That's how we are converting that all the gates as NAND. So this is what the step. So the A, B bar, as I told, we have to put one bubble. So if I put a bubble, then to compensate for that, we have to put an inverter. That's what this inverter. Similarly, B and D, that is also a AND gate here. So that we are converting into a NAND. So we are inserting one bubble in the output side. So to compensate for that, we have to put an inverter. Then here, next gate here is OR gate. That OR gate, we have to put bubble in the input side. So when I put bubble in the input side, to compensate for that, we have to insert two inverters. That's what we are doing here. So these two inverters. So this actually forms a OR gate. Similarly, another OR gate is here in the output side, this OR gate. So for that, here we are having this bubbles in the input side and we are putting inverter to compensate for that. And here this AND gate. So we are putting bubble in the output side and we are putting an inverter. So here if you see, this is inverter and this is also inverter on the same line. So that can be cancelled. So that can be removed because A double bar is A. Similarly, here these two AND gates, these two inverters, that can be again cancelled. And here this inverter is there. So we need that inverter. So we have to either we have to put an inverter or we can just have it as a bar as the input to this OR gate. This is how we are getting as a NAND implementation. So as you see here, the first just for that convenience only we are putting number. So this AND gate 1. So A, B bar, that's what we are putting here. Then B and D, the second gate, B and D, that we are putting here. These two inverters gets cancelled, these two inverters gets cancelled, as I already mentioned. Then for A, we have to give through an inverter, so we have to write as A bar. Okay. Then for the fourth here, this C, that C directly we will be giving here, and this output we will be giving to this fourth gate. That's what here, this output we are giving through the fourth gate. Then the last gate, fifth gate, here these two inverters gets cancelled. Similarly, these two inverters gets cancelled. So this fourth gate output is directly given as input, one input of the fifth gate. That's how we are forming NAND gate. So now this expression A dot B bar plus C into A plus B dot D, that expression is implemented only using NAND gate. This is how we have to implement using NAND. Similarly, we can use NOR gates also to implement the same expression. Let us see how we are going to do that. Before that, we will be seeing how to implement NOT gate, OR gate and NAND gate by using only NOR gates. So again, NOR gate has two inputs, but inverter means only one input. So what we will do is just we will short both the inputs. So it is A plus A the whole bar, that is nothing but A bar. Here to implement OR gate output is A plus B. But NOR gate output is A plus B the whole bar. So what we need to do is we have to add one NOT gate. That is, we will be using a NOR gate as a NOT gate. Okay. So that's how we are getting this A plus B. That is A plus B the double bar, you will be getting A plus B. Similarly, to implement AND gate using NOR gates, first we have to invert A and B using again NOR gate as a NOT gate. you will be getting A bar and B bar. This NOR gate, what it will do is, it will add and takes the complement. So A bar plus B bar the whole bar, that is nothing but A double bar dot B double bar using De Morgan's law. So you will be getting A dot B. A dot B is the AND operation. So using 3 NOR gates, we can implement a AND gate. And next is how to implement a boolean expression using NOR gate. Let us take that same expression, A dot B bar plus C into A plus B dot D. The first step is AND OR implementation, which we already discussed. Next step is we have to convert into NOR. So for this AND gate, we have to put bubbles in the input side, and to compensate for that, we have to put an inverter, or in other words, a AND gate can be implemented using 3 NOR gates. That's what we have seen just now. Similarly, for this OR gate, we have to put bubble in the output side to make it as an NOR. To compensate for that, we have to put an inverter. So for AND gate, we have to put bubble in the input side. For OR gate, we have to put bubble in the output side, and accordingly we have to insert inverters or the NOT gates also. That's how we are doing here. So this is the first gate, AND gate. Okay, so we are AND gate using 3 NOR gates. We are using this AND, or we are implementing this AND. Similarly here also. So first A B bar and 2 inverters are the 2 NOT gates. Similarly here 2 NOT gates, B and D. Okay, then here this OR gate means 1 NOR gate, again bubble, then to compensate for that, inverter. 2 NOR gates, using 2 NOR gates we can implement OR gate. That's what we have seen. So similarly here also, right? So here another OR gate, so 1 NOR gate with an inverter, AND gate, input side 2 inverters. So now if you see, here we need an inverter. So A should be passed through an inverter, and that should be given as the input to the first gate. So we will be getting here A bar, and here B bar already is there. So now we have to give B. Similarly here B and D we have to pass through an inverter. So we have to give B bar and D bar as the inputs to the second gate. So second gate we have to give B bar and D bar. Here we have to give A bar B. Similarly for the third gate, here we are giving A as the input, then B dot D, so that directly you give here A and this whatever it's coming here. Then for the fourth gate, third gate output, and 2 inverters are there, so that gets cancelled. So third gate output directly we can give to the fourth gate, and the C we have to pass through an inverter, so we have to give as C bar. That's what fourth gate. Then finally here this output we are giving to a fifth gate. Okay, that's what we are doing here, fifth gate, and this one. And then finally fifth gate also we are having the inverter finally, that is the sixth gate we have to implement. So that sixth gate here we are drawing as a inverter. So that we will be getting this expression A dot B bar plus C into A plus B dot D. This is how we have to implement a boolean expression using NOR gates. Then next set of gates are exclusive OR gates, derived gates. First let us see exclusive OR gate. XOR gate output is A bar B plus A dot B bar. A bar dot B plus A dot B bar. So this is the logical symbol. One OR gate, again another one extra ARC. And this is the truth table of exclusive OR gate. Here as you see, when both are equal, you are getting 0 as the input, and when both are different, output is 1. Next set of gates are exclusive NOR gates. NOR gate, the boolean expression is A dot B plus A bar dot B bar. Here the symbol is XOR gate symbol with a bubble in the output side. So this is exclusive NOR, that is XOR and with the complement. The expression is A dot B plus A bar dot B. Table of exclusive NOR gate is given below. Here as you see, when both inputs are 0 and both inputs are 1, your output is 1. Means if both inputs are equal, output is 1. When both are different, output is 0. Thank you.